you for the introduction. Good morning. My name is Georgios, and this is work that has been done in collaboration with Alvaro Alhambra, who's a postdoc at Perimeter Institute. Nayeli, who's right there, is a PhD student at the Institute for Quantum Computing. Jamie Sikora is also a postdoc at PI, and finally, Eduardo Martinez is a professor at the University of Waterloo. So thank the organizers. I would like to thank everybody for giving me the opportunity to share our work here. Okay, so let me start by setting what is the theme of the talk. So in the macroscopic regime, energy flows are governed by the usual laws of thermodynamics. And by that, I just mean that, for example, in equilibrium, energy flows from hot to cold. However, in the microscopic regime, where quantum correlations might be of importance, energy flows can be affected. And what I'm going to talk about is exactly the impossibility of energy extractions by means of local quantum operations. So this is an example of absence of energy flow, although strong coupling might be present. And the main result we have is necessary and sufficient conditions for this to happen. So let me start from the beginning and define things carefully. So let me remind everyone what is the passive state. So assume you have a quantum system with some Hamiltonian, and let's say the state undergoes some unitary transformation. You have a new state, you have a new energy in general. So the state is passive. Actually, the pair Hamiltonian state is passive if the final energy is always more than the initial energy, no matter what unitary transformation you do. So you mess with the system unitarily, you raise the energy. It's impossible to extract it. An example of that is thermal states. Okay, so let me change gears just for a moment before coming back to passivity. So in many-body quantum systems, there is more than a matrix diagonalization. And the reason for that is there's another important structure, is the one of locality. So Hilbert space carries tensor product structure, and Hamiltonians are local. So the reason I'm bringing this up is the following. Assume you want to define a new notion of passivity that is stronger with respect to not just unitary transformation, but general CP maps, quantum operations. So if you do that without any constraint, this notion is trivial. And the reason is, you can ask, what are the states such that they're passive, you cannot extract energy with respect to all CP maps? This is trivial because you can always map the state to the ground state. However, there's a nice interplay if you bring locality, and the reason is you can ask the question, what are the states that are passive with respect to CP maps, but they're maps that are local now? So let me illustrate further what I mean. Assume you have like a many-body system, like here are 6 pins, and described by Hamiltonian, but and then you want to ask the question, what are the states that are passive? You cannot extract energy. And the operations you allow is any CP map, but not overall spins, just on these 2 spins. So the topic is to characterize these states that is impossible to extract energy by local operations. So before moving on and giving you the exact definition, let me give some physical motivation why such maps might be there in the first place. So a scenario would be you have a many-body system and you want to extract energy, and the way to do that, a way to do that, would be to couple with, let's say, these 2 spins, with strong coupling and for short time scales. And if time scales are short enough such that you can ignore the free evolution of the system, what you get in the end is a map that is local. So now I can give the definition. So you have some bipartite Hilbert space with a Hamiltonian. So I will say the pair Hamiltonian state is CP local passive with respect to operations on the A part of the system, if no matter what local map you do on part A, the energy stays the same or is more. So in other words, it's impossible to extract energy. This notion was introduced by Frey, Gerlach, and Hotta in 2013. And for the rest of the talk, I'm going to focus on thermal states until at least the last part where I'll give you the general result. So now that I have defined what I'm going to talk about, let me give you some results. So I think the most natural question one can ask is, okay, and when does this happen? What are sufficient conditions to get this impossibility for energy extraction? So here is one set of such conditions. So consider some Hamiltonian in the bipartite Hilbert space. And let's say this Hamiltonian satisfies two conditions. The first one is that it is non-degenerate, namely the unique ground state. And the second one has to do with correlations. And it is that the entanglement is Max Frank. And by that, I mean if you perform the Smith decomposition over the bipartition, all the coefficients are non-zero. So given this assumption, one is guaranteed to have CP local passivity for thermal states of this Hamiltonian at low enough temperature. And by that, I mean there is a threshold temperature, let's call it threshold temperature, such that all thermal states that are cooler than that have this CP local passivity. Namely, it's impossible to extract energy by local operations. So this result was shown by Frey, Funo, and Hotta 2014. Our result is an extension to that, and the first thing we did was to actually give an estimate, give a bound, what is this temperature. So here's our relation. So what one can do is employ that and plug in what is the Hamiltonian and get an estimate for what is this critical temperature. And then one is guaranteed that anything colder than that, as given by the bound, is a CP local passive. Okay, here's an example. I'm a bit short on time, so I'll go fast. So this is a 2-qubit Hamiltonian, is A and B. Let's say one acts on A, and the kappa is the coupling strength, is the horizontal axis. And the two curves you see numerically, the gray is the critical temperature as given by the exact solution, and the black is the bound. So you see the bound captures in that case the behavior of this temperature. Okay, so another question that one could ask is what happens in the thermodynamic limit, and why is that of relevance? Is because it's not clear from what I have said whether this phenomenon could persist if one has, for example, a large thermal bath. Many particles, many degrees of freedom in a thermal state. So the first thing one can do is actually apply the bound and see what it gives, but it turns out it trivializes for when one sends the particle numbers to infinity. So, nevertheless, there's this intuition on the other side that if one has weak spatial correlations, namely two spins far away are not much correlated, then it doesn't matter if you go to the thermodynamic limit. If you fix the region you act upon with your CP map, then just adding particles far away shouldn't matter. So to get something out of this intuition, we use the definition of clustering of correlations. So I'm not going to guide you through, but the idea is simple. Is a state has clustering of correlations if for observables far away, the error you do by assuming the expectation values factorize is bounded by this function epsilon of L. And for large L, weak correlation means this decays, so you can safely assume things factorize. So the result is this one, but before I have to tell you what is the setup. So quickly, in the center, there is the region S, where the system is where the CP map act upon. There is region A, which includes this part. And then the rest we call B. B has two parts, though, B1 and B2. So skipping the technicalities, the idea is this one. So you have this freedom B1 and B2, and your goal is to satisfy this inequality. If you do that, then you're guaranteed to have CP local passivity for the whole system. but the left-hand side is related to CP local passivity only in the region AB1, which you can take to be not infinite, you can have to be finite. And the other side has to do with the clustering of correlations. You see there's this epsilon of L. So the idea is you can choose this interface B1, not too small, such that the left-hand side, the right-hand side is satisfied, but not too large either, so the left-hand side does not trivialize. Okay, so this is how we deal with the thermodynamic limit. So the intuition is systems with weak clustering still experience CP local passivity in thermal state for even if the particle number is infinite. So this is my last result. So as I promised at the beginning, we have more than sufficient conditions. So here are a set of necessary and sufficient conditions. And the machinery behind that is semi-definite programming. So I don't have time to guide you through the details, but the result is, instead of optimizing over all possible CP maps, like the definition wants, one can check this matrix inequality. This is a matrix that is a function of the Hamiltonian and the state that is completely general. Any Hamiltonian, any state. Doesn't have to be thermal, for example. And if the matrix is positive, then the state is CP local passive. If not, then it's not. So it's necessary and sufficient. So I have to conclude. I talked about this phenomenon of CP local passivity. And the idea is that it's an example of impossibility of energy flow, although there is stroke coupling. And this happens because of quantum correlations. So I talked about how Max-Rack entanglement and unique ground state can imply CP local passivity in low temperatures. How sufficiently weak spatial correlations can extend this notion to the thermodynamic limit. And finally, I gave you the necessary and sufficient conditions very briefly. Thank you.
Thank you. So we're open for questions, yeah?